Dear all, good morning. Now our lecture is reduction of quadratic form to canonical form by orthogonal transformation. Now we'll discuss what is the quadratic form to canonical, how to convert it to quadratic form to canonical form. Last class we discussed quadratic form. What is the quadratic? We discussed this one. Quadratic form we denoting q of x equal to summation I is equal to 1 to n, summation j is equal to 1 to n, aij, xi, xj. Same as you can write x transpose ax. When you are expanding this one, we are getting like this a11 x1 square, a12 plus a21 x1 x2 plus a22 x2 square and so on. a13 plus a31 x1 x3 like that. Now this one x1 x2 term, x1 x3 x2 x3 term is there. The term is called cross term. But the quadratic form without cross term, the form is called canonical form or normal form. You can write definition. A quadratic form without contains cross term. Quadratic form without containing cross term. Cross term. The transformation is the form is called, or the quadratic form is called the quadratic form is called canonical form, or you can say normal form. Canonical form, or you can say normal form. See now, what kind of cross term is there is no x1, the product of x1, x2, x2, x3. If quadratic means degree 2, that means there is no cross term, only it's sum of squaring terms. That means a11 x1 square, a22 x2 square, and so on. Right? Yeah, that means q of x, this is the x transpose ax. This is transformed to summation. You know, this is the summation I is equal to 1 to n, j is equal to aij, xi, xj. This is transformed to I is equal to 1 to n from aii into xi square. Some real number. This one converted to like this using some orthogonal transformation. Now we'll see what is the orthogonal transformation. Yeah, this is the canonical form. Then is a quadratic form. Convert to quadratic form to canonical form by using orthogonal transformation. Before see orthogonal transformation, already we discussed diagonalization. When A is n by n matrix, diagonalizable means we can write if A is diagonalizable, A is diagonalizable means A is equal to d p inverse, or P AP equal to PD. AP equal to PD. Already know this one. A is diagonal. Suppose A is a symmetric matrix. Already I told you if A is symmetric matrix, the diagonalization is orthogonal diagonalization. If A is symmetric, the diagonalization is orthogonally diagonalization. Because we are writing, we are getting symmetric matrix corresponding given quadratic form. We are symmetric matrix. But symmetric matrix, already this one when the symmetric matrix, but P D are same as the P transpose. P is same as the P transpose. Okay, this is the orthogonal diagonalization. Because a symmetric corresponding eigenvectors, they are mutual corresponding eigenvector with respect to distinct eigenvalues are mutually orthogonal. mutually orthogonal, we can write orthonormal vectors expanding each eigenvector is orthonormal vector. Yeah, the orthonormal vector, if you write columns orthonormal vector, the columns are in, suppose you are writing P columns of orthonormal vectors like x1, x2, now x2. This is the orthogonal matrix. Orthogonal matrix. Usually we are denoting orthogonal matrix is Q. That's why I am writing this using transformation QD, Q transpose you can write. Generally we are using orthogonal, you are writing orthogonal matrix is Q. The one. If it is distinct, if equal eigenvalues, we are getting linearly independent vector. If you know linearly independent vectors, corresponding linearly independent, we can find the orthogonal vectors by using Gram-Schmidt process. Already I told you every symmetric matrix is the diagonalizable. Distinct directly it's orthogonal diagonalizable. Not distinct, we can find the orthogonal matrix by using Gram-Schmidt process. Now we'll see what is the x equal to qy. Here q is the orthogonal matrix. This is the transformation. This is the orthogonal transformation. X equal to qy. Orthogonal matrix. This transformation is called orthogonal transformation. Transform the matrix. Transform the quadratic form. Q of x. X transpose ax. The canonical form. Canonical form means there is no cross term. Only y1 square. Here y is the vector. y1, y2, y3 like. The qx is set to reduce to the canonical form by an orthogonal transformation. This is the orthogonal transformation. What is the orthogonal? Q of x, we know this quadratic form is x transpose x. The orthogonal transformation. Orthogonal transformation. Orthogonal transformation x equal to qy. When you take x equal to qy, therefore q of x equal to x is qy. Now substitute here. Qy transpose a x is qy. The same as if expand this y transpose q transpose a qy. Here a is a symmetric matrix. Already I told you a symmetric matrix is orthogonally diagonalizable. You can convert it to orthogonal diagonalizable. Now here we written a equal to pd trans or qdq transpose. What about d equal to here? We written a is equal to qd q transpose. Suppose if you pre-multiply and post-multiply q transpose aq, this is equal to q transpose q is identity. This is id and q transpose q also identity. That means q transpose aq we get diagonal matrix. That means y transpose d y. Now y is equal to suppose whatever y1. Suppose if you take n by n matrix yn, that n variables. Suppose we take n variable x. This is equal to that means y1 transfer y1 yn diagonal matrix. Suppose take lambda 1 0 and 0 0 lambda 2 0 lambda diagonal d1 d11 d12 dnn diagonal matrix diagonal elements and y1 y2 and yn. Multiply this one the same as the will get d11 y1 whole square d22 y2 whole square plus dnn yn square. This form is called canonical form. We are reducing quadratic form to canonical by using orthogonal transformation. That is the reducing quadratic form to canonical form by using orthogonal transformation. Now we'll see the same as that one. So now what the procedure? To remember this procedure, how to find this canonical form by using orthogonal transformation. So to reduce quadratic form to canonical form, by orthogonal transformation. See, first point, to write the matrix, write the symmetric matrix. Symmetric matrix associated with given quadratic form. Given quadratic form. Given quadratic form. Yeah, first write the matrix. Second point, find the eigenvalues and corresponding eigenvector. Find the eigenvalues and corresponding eigenvectors of A. Next, third, you have to form the orthogonal matrix. Form the orthogonal matrix Q containing the orthogonal matrix containing orthonormal eigenvector or normalized eigenvector, you can say normalized eigenvector containing normalized eigenvectors of A. This one. Yeah, normalized eigenvectors of A. Then if x equal to qy, qy gives the required orthonormal transformation. This is give required orthonormal transformation. Orthogonal transformation. Orthogonal transformation. This transform which reduces, reduces quadratic form to canonical form. Quadratic form to canonical. This is a procedure. Remember this steps. So write the symmetric matrix, find the eigenvalues and eigenvectors. Now first to find the orthogonal transformation. This transform which gives quadratic form to canonical form. This transform reducing quadratic form to canonical form. Now see example. It is the quadratic form, the canonical form by an orthogonal transformation. The solution. The symmetric matrix. First write this first part symmetric matrix A corresponding or associating given quadratic form. Last class we discussed how to write the matrix corresponding the quadratic form. A equal to, we get the squaring terms are diagonals. Here x, y, z is there. Plus of x1 is x, x2 is y, x3 is z. X vector is the like x, y, z. Let q of x equal to given quadratic form x square plus 2y square plus z square minus 2xy minus 2yz. Same as x transpose x, where x is xyz. The symmetric matrix A corresponding to the corresponding given quadratic form is A equal to this is the xy coefficient, minus 2, now half minus 1. Next to xy yz. No, first one is this xy. Now xz, there is no term xz, that is 0. This is same as minus 1. Y square term yz. Yz is minus 2, that's minus 1. 0, minus 1, z cube. The symmetric form. Now find the eigenvalues. Already we know how to find the eigenvalues and eigenvectors. I'm not finding, I'm writing directly. I'm writing the eigenvalues of, right, the eigenvalues. I write, find the characteristic equation and find the roots. They are eigenvalues. I'm writing directly the eigenvalues of your lambda equal to 1, 3, 4. Now eigenvectors, already you know finding eigenvector corresponding lambda equal to 1. Eigenvector means we get a minus I x equal to 0. Yeah, now solving this system, we get the eigenvector. We get eigenvector x1 is 1, 0, minus 1. Similarly, eigenvector lambda equal to 2 is lambda equal to 3. I'm writing directly lambda 3 x2 equal to 1, 2, 1. And eigenvector, I'm writing directly the eigenvectors and eigenvalues. Lambda equal to 4 is x3 equal to 1, minus 1, 1. Now observe here, one is x1 is 1, 0, minus 1. This A is the symmetric matrix. A is the symmetric matrix. Already you know symmetric matrix corresponding eigenvectors with the distinct eigenvalues are mutually orthogonal. Mutually orthogonal. Now observe here, these are the orthogonal. x1, x2, 0, x2 dot x3 0, x3 dot x1 also 0. If orthogonal vector, we can write orthonormal vectors. The matrix Q is the normalized vector. Normalized vectors. Vectors are normalized means how to divide each vector with length. x1 equal to what is the length? Root 2. 1, 0, minus 1. Now x2 by norm x2 is 1 by 4, 6. 1, 2, 1. And x3 by norm x3 equal to 1 by root 3. And x3 by norm x3 equal to 1 by root 3. 1 minus 1, 1. The normalized vectors or orthonormal vectors, orthonormal eigenvectors, or you can say normalized eigenvectors or orthonormal vector eigenvectors. Therefore, orthogonal matrix Q equal to the one x1 by norm x1, x2 by norm x2. Don't write commas. The matrix x3 by norm x3. This is the orthogonal matrix. This right first one 1 1 by root 2 0 minus 1 by root 2 1 by root 6 2 by root 6 1 by root 6 1 by root 3 minus 1 by root 3 1 by root 3 and Q transpose equal to 1 by root 0 minus 1 by root 2 1 by root 6 2 by root 6 1 by root 6 1 by root 3 minus 1 by root 3 1 by root 3. Now this is the orthogonal matrix. The orthogonal transformation is take the orthogonal transformation. We said x equal to qy, where y equal to can take y1, y2, y3. Yeah, therefore now qx. Now you have to convert to this quadratic form. That is x transpose x. We are taking x equal to qy. We know this one qy transpose a qy. The same as the y transpose q transpose a qy. Orthogonal transformation. This is y transpose dy equal to y transpose. Or the y transpose is y1, y2, y3. Now whatever you write eigenvector first column, you have to take corresponding eigenvalue. This is 1. Okay, second eigenvector corresponding eigenvalue is 3, 4. That is 1, 0, 0, 0, 3. The order is important. If you are eigenvectors you are writing interchange, here you have to eigenvalues also interchange. Into y3. This is equal to, if you multiply this one, you get y1 square plus y2 square plus 4 y3 square. This is a canonical form. Canonical form. Yeah, now we are reducing quadratic form to canonical form. Suppose it starts asking find the orthogonal transformation. Yeah, suppose you are find the orthogonal transformation. The orthogonal transformation is x equal to qy. That implies x is x, y, z. Q. Now write q. For the q is 1 by root 2, 0 minus 1 by root 2. 1 by root 6, 2 by root 6, 1 by root 6. Next 1 by root 3 minus 1 by root 3, 1 by root 3 into y. Y is y1, y2, y3. Now two matrices are equal. This implies x, y, z equal to, now multiply this one. This is 1 by root 2 y1, 1 by root 6 y2, 1 by root 3 y3. 1 by root 2 y1 plus 1 by root 6 y2 plus 1 by root 3 y3. Next 0 y1 and 2 by root 6. 0 plus 2 by root 6 y2 plus minus 1 by root 3 y3. Next minus 1 by root 2 y1 plus 1 by root 6 y2 plus 1 by root 3 y3. This implies now matrices are equal. Corresponding elements of that implies x equal to y1 by root 2 plus y2 by root 6 plus 1 by root 3 by 3, and y is equal to 2 by root 6 y2 minus 1 by root 3 by 3, and z equal to minus 1 by root 2 y1 plus 1 by root 6 y2 plus 1 by root 3 by 3. Now using this transformation, suppose you are substitute x equal to this transformation, x y1 by root 2 y2 by root 6, 1 by root 3 by 3, and y equal to 2 by root 6 y2 minus 1 by root 3 by 3, and z equal to this one. In the given quadratic form, that one is converted to if you substitute this in given quadratic form, this equation, if x equal to y is equal to z and x y z, now this is converted to canonical form. This one to this canonical form. If it's asking find the orthogonal transformation, that one. Otherwise, just asking quadratic form to canonical form, you have to convert it up to here. You have to find the canonical form. That's the sum of the squaring terms. There is no cross term. So, now see another example. Example 2. Right, find the canonical form of the quadratic form from x1 square x2 square plus x3 square plus x1 x2 plus 2 x1 x3 plus 2 x2 x3. Find the canonical form of the quadratic form by using, sometimes it's not mentioned, by using orthogonal transformation. If not mentioned, you have to use orthogonal transformation. In our course, we are discuss only converting orthogonal quadratic form to canonical form, only orthogonal transformation. You can go for another method also, but here we are discussing only one of the method, orthogonal transformation. If mentioned or not, you have to use this orthogonal transformation. Now solution. Given quadratic form is from q of x equal to x1 square plus x2 square plus x3 square plus 2x1 x2 2x1 x3 x2 x3. The symmetric matrix A associated with q of x is A equal to x1 1 x1 x2 coefficient, top one is 1, x1 x3 is 2, the top one, this is 1, then x2 square 1, x2 x3 of 1 1 1 1. This is the matrix. Now already we discussed this matrix. We know eigenvalues. The eigenvalues of A are, I am writing directly, the eigenvalues of A are 0 comma lambda equal to 0 comma, yeah, 0 0 3. That means, okay, right, 0 0 0 repeating 2 times, 0 0. Now eigenvectors corresponding are equal to 0. Already we know this, we are getting eigenvector, 2 eigenvector or minus 1 0 1. So take x1 equal to and x2 equal to minus 1 1 0, and eigenvector corresponding lambda equal to 3 is 3 equal to 1 1 1. These are the eigenvectors. Now you can check these are not mutually orthogonal. x1 x3 orthogonal, x2 x3 orthogonal, but x1 x2 are not orthogonal. These vectors are not orthogonal. But they are linearly independent. If you are this linearly independent, by using Gram-Schmidt process, we can find orthogonal vectors. By Gram-Schmidt process, we can find Orthogonal. If you know orthogonal vector, we can write orthonormal vector, and we can find orthogonal vectors. Let x1 x2 x3. Suppose let take w1 w2. Then we are using here. Okay, you can take v1 v2. Let v1 comma v2 v3 are orthogonal vectors. Now, what the v1 equal to vector? Generally, we are taking here u1 u2 u3, here x1 x2 x3. That x1 x1. Now, what the v2 equal to? x2 minus inner product of x2 v1 divided by norm v1 square into v1. Now x2, what the x2 is? Minus 1 1 0. Inner product of x2 v1. This is the, okay, whatever, right? Minus 1 0 1 transpose. Now inner product, what about this one? Minus 1 into minus 1 1. That's 1 divided by 2. Root square root is 2 into minus 1 0 1 is equal to minus 1 plus 1 by 2, minus 1 plus of minus of 1 0 minus of, this is minus of, is equal to, you can write of, you can take common, it's minus 1 2 1 2 minus 1, this is 1, and v3 equal to x3. We know this x3 v1 by norm v1 whole square into v1 minus x3 v2 norm v2 whole square v2 is equal to x3. What the x3 is 1 1 1 minus x3 v1 orthogonal, that is 0 0 by something is 0 minus x3 v2 x3 v2 x3 v2 is 1 1 1 x3 v2 1 minus 1 by 2 minus, okay, minus 1 by 2 plus 1 minus 1 by 2, again it's 0. Am I correct? Minus 1 by 2 plus 2 by 2 1 minus 1 by 2 is 0. That means therefore orthonormal eigenvectors. So orthonormal eigenvectors. Suppose take w1 equal to v1 by norm v1. This is the 1 by root 2 into minus 1 0 1. w2 equal to, take v2 by norm v2 is equal to, determine 4 6 1 by root 6 into minus 1 2 minus 1 transpose, and w3 equal to v3 by norm v3. This is 1 by root 3 into 1 1 1. So if any doubt, you can check this. Must be orthogonal. The length is 1 each one. Now minus 1 0 plus 1 is 0. Minus 1 plus 2 minus, this is 0. Whatever this one is 0. This is the one of the way. Otherwise, you can find another way also. So already you know this x1 x3 and x2 x3 are orthogonal. X3 is orthogonal to x1 and x2. Now it's and another vector orthogonal to x1 and x2. Suppose another vector orthogonal to x1 and x2. Suppose if suppose u is orthogonal to x1 and u is orthogonal to x2. Whatever you take. Now use the relation inner product and find the u. This is orthogonal to x1 and x2. orthogonal to x1 and x2. But that one also must be orthogonal to this x3. This is not okay. Better to, yeah, already you know this orthogonal. Only it's enough to find this one by using Gram-Schmidt process. One is that one, another one find the Gram-Schmidt. Already you know, no need to go for V3. Already you know this is orthogonal to x1 and x2. Just to find apply Gram-Schmidt for x1 and x2 only. It's enough. Here I use x3, but no, it's no need. Because already we know this x3 is orthogonal to x1 and x2. Just apply Gram-Schmidt process for x1 and x2. It's enough. This one. Now, therefore, orthogonal matrix is Q equal to, we are taking orthonormal vectors are like this one. This is equal to minus 1 by root right columns transpose 0 1 by root 1 minus 1 by root 6 by root 6 minus 1 by root 6. This 1 by root 3 1 by root 3 1 by root 3, and Q transpose equal to minus 1 by root 2 0 1 by root 2 minus 1 by root 6 2 by root 6 minus 1 by root 1 by root 3 1 by root 3 1 by root 3. This amount. Hence, okay. Now you have to convert to quadratic form to canonical form. Take orthogonal transformation. Take orthogonal transformation. X equal to qy, where y is equal to take y1, y2, y3. Hence, q of x, x transpose ax. This is converted to direct. You can write this is the y transpose dy, where x equal to qy. This is okay. y1, y2, y3. D is now must be whatever we written first vectors corresponding 0 eigenvalue. That means you have to write 0 eigenvalues for first 0 0 0. Next last we written last column of q. This is equal to 0 into y1 square plus 0 into y2 square plus 3 into y3 square. The same as 3 into y3 square. Only one term. This is a canonical form. What the we talking? What the orthogonal transformation is? X equal to qy. Now substitute x qy. This is the orthogonal transformation. Yeah, this is the way to find the canonical form. That is reducing quadratic form to canonical form by using orthogonal transformation. This is the procedure. Just to remember what is the procedure. First to write the quadratic equation. First to write the symmetric matrix given quadratic equation. Next is how to find the eigenvalues and eigenvectors. After finding eigenvalues and eigenvectors, how to find the orthonormal vectors. Orthonormal vectors. Now I stop here. Thank you.